right, well, we've still got folks filing in, but let's go ahead and get started.
All righty, welcome everybody to the 10:15 a.m. Mountain Time, or 12:15 Eastern Time. It would be 10:15 a.m. if we were all in Salt Lake City, but unfortunately we aren't. To this press conference called Evolving Stars and Their Activity. I'm Haley Wahl. I'm the AAS Media Fellow and also a grad student at West Virginia University, and I will be your MC today. Joining me, we have Macy Huston, who is the Astrobites media intern, also a grad student at Penn State, who will be assisting with Q&A. And we've also got Susanna Kohler, who is the AAS press officer, and Carrie Hensley, who is the AAS deputy press officer, who will be dealing with any technical issues that come up and helping with the press releases. So there will be 3 press releases distributed today, one from each presentation. Yesterday's videos they should be all up online, and the press kits have also been updated with the links to the presentation files and the press releases, so you can check the AAS website. A couple of ground rules. Today we're going to be recording this briefing and also streaming it live to YouTube. We have 3 speakers today. We have Andrew Nine from the University of Wisconsin-Madison with a presentation titled Detection of White Dwarf Companions to Blue Lurkers in Star Cluster M67. And then we have Sam Swihart from the Naval Research Lab with a presentation titled A Unique Gamma Ray Bright Neutron Star Binary with an Extremely Low Mass Proto-White Dwarf. And then finally, we have Bradley Schaefer from Louisiana State University, Baton Rouge titled Discovery of Extreme Superflares on Recurrent Nova V2487 Ophiuchi. So the speakers will speak in order with no downtime between them, so they'll just go one after the other. Attendees, please type your questions in the cute little Q&A box, and please note your name and your affiliation. And speakers, please, the speakers are not going to be answering the questions in the Q&A just because we're streaming live to YouTube and they can't see in the Q&A. Feel free to upvote questions that you think are relevant to raise their priority in the queue. So again, this presentation is titled Evolving Stars and Their Activity. And today I'm going to turn it over to the speakers.
All right. Okay, I'd like to first take the opportunity to thank the organizers for this opportunity to present our results. My name is Andrew Nine. I'm a graduate student at the University of Wisconsin-Madison, and I am very happy to present our results on the detection of white dwarf companions to the blue lurkers in M67, which I've conducted in collaboration with my advisor, Bob Matthew, and our collaborators, Natalie Gosnell and Emily Liner. Now, to understand the blue lurkers in M67, we must first discuss the classical blue stragglers. Now, I've copied here on the right a color magnitude diagram of the open cluster M67, and I've highlighted a few stars in particular. The classical blue stragglers, as we can see, are bluer and brighter than the main sequence turnoff of this cluster. Now, these defy our understanding of single stellar evolution because in single stellar evolution, the lifetime of a star is determined almost exclusively by its mass. And the more massive the star is, the shorter its lifetime. So these stars are more massive than the turnoff and should have therefore evolved away already. Yet there they are. So the explanation for these stars are, of course, binary stellar interactions. And we think these stars form through 3 pathways, which are stellar collisions, the merger of inner binaries, for instance, in a hierarchical triple system, or through mass transfer from an evolved companion star. So the blue stragglers stand out instantly in a color magnitude diagram. However, the blue lurkers are a different story. The blue lurkers, which I have highlighted here, can be found all throughout the main sequence of the cluster, and at first glance, they do not appear remarkable at all. However, these stars were first discovered by Liner et al. 2019 on the main sequence of M67. These are discovered as part of the ongoing WIN open cluster study. And these stars are discovered because they are anomalously rapidly rotating, with rotational periods between 2 and 8 days, which correspond to gyrochronological ages of less than about 1 billion years, substantially younger than the surrounding cluster. Now, as stars age and evolve on the main sequence, their rotation periods tend to slow down. Now, if you know how fast the star is rotating, you have a good estimate of how old that star is, and that process is referred to as gyrochronology. Now, through this process, 11 blue lurkers were discovered, 8 of which are in binaries with periods ranging between 100 and 10,000 days. And those binary periods are much longer than would be plausible in order to spin up these stars through tidal interactions. So something else must have happened to these stars to make them spin as fast as we see them today. So in order to determine what exactly happened to these blue lurkers, we conducted far ultraviolet observations of these blue lurkers with the Hubble Space Telescope Advanced Camera for Surveys in the solar blind channel. We observed these blue lurkers in 3 far ultraviolet broadband filters, f140 LP, which is focused at 1400 angstroms, f150 LP, which is focused at 1500 angstroms, and f165 LP, which is focused at 1650 angstroms. We also exploited the nested structure of the band passes to derive narrowband filters, which more cleanly isolate the far ultraviolet flux of these blue lurkers. And I have here on the right an example of the data we collected from the Hubble Space Telescope. We can see this particular blue lurker walks 14020 right there in the middle of the frame. And as for, yes, and we computed magnitudes for each blue lurker with aperture photometry, adopting a aperture radius of 1 arcsecond. And as for our results, I have here our detections of the blue lurkers. So this dashed black line, this is what we would expect a typical main sequence star in M67 to appear to Hubble Space Telescope using our magnitude scheme. And the black points here are our measured photometric results. And the color contours represent 1, 2, and 3 sigma respectively. And as we can see here, we have 2 confident detections. WOX 3001 you can see just to the blue of the main sequence, and WOX 14020, which is well separated from the rest of the main sequence. And for comparison, I repeat here our optical color magnitude diagram. We can see 3001 is relatively bright, but not brighter than the turnoff, but substantially hotter. And WOX 14020 is well down the main sequence. It is essentially a sun-like star, yet clearly in ultraviolet, something is up. So in order to better understand the companions to these blue lurkers, we first had to get a handle on the temperature of the blue lurkers themselves, which we did by fitting Castelli-Caruch model atmospheres to any available optical and infrared photometric measurements. And we derived effective temperatures for WOX 3001 and WOX 42020. Again, the 2 blue lurkers with significantly aberrant ultraviolet results. And then we generated a UV blue model atmosphere for the blue lurkers at these derived effective temperatures. And we also generated Kester 2010 white dwarf model atmospheres, which we were scaled, assuming a distance to M67 of 850 parsecs and a radius of about 0.02 solar radii. And if these were helium white dwarfs, which is possible, these correspond to masses of about 0.45 solar masses. And we then found the best fit combination of blue lurker and white dwarf models by incrementing the effective temperature of the white dwarf model to fit the available UV data. Now, I know this is a lot of jargon. The main takeaway from this slide that I want you to receive is that what you're about to see are best fit models to our available photometric measurements. So the photometry is what we observe, and the lines you're about to see are best fit models, which you can see here. So on the left-hand side, I have plotted our results for WOX 14020, which is the one most significantly detected in the far ultraviolet. And we find a best fit white dwarf temperature of 12,500 Kelvin. And I've plotted here in pink our Hubble ultraviolet measurements, and in red our measurements from GALEX. Now the gray boxes I have plotted here, the widths of these gray boxes are the band passes themselves, and the vertical extent of these boxes are the uncertainties on the photometric measurements based on the uncertainties of both the blue lurker and white dwarf effective temperatures. And the same you can see on the right, corresponding for WOX 3001. The blue is the model atmosphere, orange is the white dwarf. Again, pink is Hubble. And I've also included here the red galaxy measurements, and in green, I have plotted the results from Jadov et al. 2019, who also observed this star with Astrosat and UVIT, which is operated by ISRO, the Indian Space Agency. Now, all those photometric measurements agree with the presence of a white dwarf. However, the galaxy and UVIT band passes are substantially wider than our narrow band passes, and as such are contaminated by the vene tail of the primary star. However, when that is corrected, all the galaxy and UVIT measurements do agree with the presence of a white dwarf. So what does this all mean? Now, in an earlier study by Gosnell et al. 2015, who observed the blue stragglers of the older open cluster NGC 188, out of a sample of 19 observed blue stragglers, they observed 4 hot white dwarf companions, which is a detection rate of about 21%. Now, based on the N-body simulations of NGC 188 by Geller et al. 2013, who studied the formation of blue stragglers through this N-body simulation, they expected to detect about 3 white dwarfs, which is consistent with what was detected for NGC 188. Now, we detected in this work 2 white dwarf companions out of a sample of 8 blue lurkers, which corresponds to a detection rate of 25%. Now, based on the N-body simulation of the M67 blue stragglers, which are analogous mass transfer companions, this N-body simulation was conducted by Hurley et al. 2002. If we were to observe 8 M67 blue stragglers at random, we would expect it to detect about 4 plus or minus 2 white dwarfs, which is consistent with what we detected as well. Now, based on this, it is reasonable to suspect that all of the binary blue lurkers are products of mass transfer, and as such are low luminosity analogs to the classical blue stragglers. And as a few points of summary here, we observed 8 binary blue lurkers in the open cluster M67 with the Hubble Space Telescope. Out of the 8 blue lurkers we studied, we detected 2 white dwarf companions based on their far ultraviolet flux. And this detection rate is consistent with the expected detection rate based on similar mass transfer products, and it is therefore plausible the blue lurkers are low luminosity analogs to the classical blue stragglers. In future, far ultraviolet spectroscopic observations are needed to constrain the properties of these white dwarf companions. I would again like to thank the organizers of this conference and for the opportunity to present our results, and all my contact information is displayed below if you would like to follow up.
Okay, I guess it's my turn to jump right in. Thanks, Andrew. That was a nice talk. So, hi, everybody. My name is Sam Swihart. I'm a postdoc at the U.S. Naval Research Lab, and I do multi-wavelength observational astronomy, which is just a fancy way of saying that I use a lot of different cool telescopes to find cool stuff. So, I'm going to stop my video for the purpose of this talk. I was having some internet problems, so hopefully everything goes well. So I'm going to talk today about a new paper that just came out where we found a really interesting binary system with a proto-white dwarf orbiting a neutron star. Hopefully by the end of this talk, you'll have an idea about what those words mean. So although I led this paper, it took a small team of researchers to put this work out. So I'd just like to highlight some of the contributions, especially from those at Michigan State University, where I got my PhD a year and a half ago. So the main subject here is a special kind of rapidly spinning neutron star known as a millisecond pulsar. So I'm going to briefly introduce to you what that is. Unlike the sun, most stars in the universe are born in binary systems. And in these systems, the more massive star will live and evolve much faster. You may have heard the moniker live fast and die young. If this massive star is more massive than about 8 times the mass of the sun, its end fate will be to explode in a supernova, leaving behind an extremely dense core that is more massive than the sun, but only the size of a small city. These are known as neutron stars. As this neutron star rotates, we see a pulse of radiation as that radiation crosses our line of sight. This is similar to how a lighthouse spins around, and as the light crosses your eyes, you see a flash of light. This is exactly what's going on in these rapidly spinning neutron stars. So astronomers call these pulsars. So normal pulsars will gradually slow down as they lose energy over time. But in a binary system, eventually the companion will expand as it evolves. This is just like what will happen to the sun. And as this happens, the gravity from the neutron star will pull material onto its surface and spin it up to these really rapid spin periods. This is analogous to if you have a basketball spinning on your finger and you hit the side of a basketball to make it keep spinning faster. This is kind of exactly what's going on, is this material from the companion gets accreted onto the neutron star. It kind of comes in at an angle and hits the side of it, spinning it up to these really rapid spin periods. So this results in a neutron star that is now spinning hundreds of times every second, which is about once every few milliseconds. So we call these a millisecond pulsars. So before I move forward, I'd just like to mention that this is relevant to some of the research that is going on at the US Naval Research Lab, because these millisecond pulsars are extremely stable rotators, rivaling the precision of atomic clocks. So for example, if our GPS satellites were to go out for whatever reason, our ships and planes would still be able to navigate and keep time with the knowledge of the spin periods and positions of these really rapidly spinning millisecond pulsars. So now that we know what these systems are, I would like to show the current census of the binary millisecond pulsars, where here I've shown the mass of the companion on the x-axis, with the higher mass the heavier things on the right, lighter things on the left, and then on the y-axis we have the orbital period of the system, where we have wide, long orbit systems at the top and short orbit systems at the bottom. So the majority of these millisecond pulsars have white dwarf companions. These are these blue circles in this figure, which represents the end stage of this recycling process that I just talked about. A white dwarf is just what the sun will become at the end of its life. It's basically just the leftover core of a low mass star. So recently, follow-up of high energy Fermi gamma ray sources have allowed us to discover a bunch of interesting systems that aren't in these very end stage systems. So some of these have been coined spiders, since the central neutron star is actually consuming the companion, similar to how black widow spiders do in nature. These are the red and black squares I show here. Closely related to these, but maybe a little more relevant for this particular talk, is we've also found a number of these extremely low mass white dwarfs. These are these 5 or 6 blue circles that I've highlighted here at the bottom. We know that these can only be formed in binary systems. And what I would like to talk about is the discovery of a progenitor to one of these particular systems, which I'm going to refer to as J1120. So this complicated name at the top here just stands for the 4th Fermi Gamma Ray Lat catalog, and then the phone number there at the end just refers to its position on the sky. On the left here, I'm showing an X-ray image where these black smudges are individual X-ray sources and their positions on the sky relative to the position of the gamma ray source. These progressively smaller circles that you see just highlight the improved localization of this gamma ray source as we acquire more data. So this green circle that's very large, we knew that this gamma ray source was coming somewhere in this area after, this is using data from only the first year of Fermi. Fermi has now been in space for almost 12 years now. So after collecting more and more data, we're now able to better localize the source. So now we know it's coming from somewhere in this magenta circle. So there's an X-ray source in this region. And then on the right, I'm showing an optical image of this region where the inset is furthermore zoomed in, showing that the position of the X-ray source matches perfectly to a star that happens to be very blue. So we have a gamma ray source with an X-ray and an optical counterpart. That's an interesting thing. It's not super common. So we'd like to figure out what that is. And so using optical spectroscopy with the NORLAB SOAR telescope, we found that this star that's coincident with this X-ray source is actually orbiting some invisible compact object. These spectra allowed us to constrain the temperature and surface gravity of the star. That's kind of what I'm showing on the left here. But maybe even more importantly, these spectra allowed us to constrain the masses of the system by allowing us to solve for the radial velocity curve. I mentioned that this star is orbiting something invisible. We're only able to see the Doppler shifts of this star. So we can only see that it's either moving towards us or away from us. And after we take a bunch of those measurements, we're able to see that it's actually doing this periodically every 15 hours. This means that every 15 hours, this star is orbiting some object that's invisible to us. And I mentioned before that a neutron star is only the size of a small city. So this is very likely what this is orbiting. Since we don't see it, we wouldn't be able to see such a small object so far away. So a neutron star is very likely what this thing is orbiting. So I'll now bring it full circle and bring it back around to the same figure that I showed before, with now this J1120 source included. After we estimated the radius of the star, which I skipped over for the purpose of this talk, but I'd be happy to discuss how we figure that out. We find that although this companion shares a lot of properties with these extremely low mass white dwarfs, these blue circles that are close to that purple star, our source, this J1120, is actually 5 times larger than these other white dwarfs that it kind of lives near in this figure. So this is unique among the known companions to millisecond pulsars. So we ran some binary evolution models, and the results of these models allowed us to predict that the companion is still contracting. And then in about 2 billion years, the system will actually look identical to these known millisecond pulsars with these extremely white dwarfs, these blue circles that it's sitting next to. So this means that J1120 is actually the first system ever discovered in kind of this second to last phase of this pulsar recycling process. So one analogy that you can think of is if these 5 or 6 blue circles that this purple star is next to, if those systems are kind of these mature adult binary MSPs that are kind of finished growing and evolving, what we found is a system kind of in the late teenager phase. So just to summarize, we found this optical and X-ray source inside one of the brightest unassociated Fermi gamma ray sources that's still unidentified. And we used optical spectroscopy that allowed us to characterize the companion as a bloated low mass white dwarf in a 15-hour orbit around this suspected neutron star. As I mentioned, these binary evolution models predict in about 2 billion years, this system is going to look identical to the few millisecond pulsar binaries that we know of with extremely low mass white dwarfs in these short orbits. So the best way to describe what this companion is kind of a pre-ELM or a pre-extremely low mass white dwarf. It's a progenitor to these systems. So the last thing I'll say is that this system, being in this kind of penultimate phase of this MSP recycling process, kind of represents a missing link in our understanding of the final phases of the normal millisecond pulsar binary evolution. And with that, I'd like to thank the AAS press office again, and I'll shut it down. Thanks, everybody.
Brad, you are still muted and your video is off.
It says I can't start video because the host has stopped it.
Does that work? Yeah. Sorry about that.
No trouble. Well, hi, everyone. I would like to announce the discovery of extreme superflares on the recurrent nova V24870. The short story of it is that this exotic star, a recurrent nova, shows flares on it. These flares typically come once a day and they last for about an hour. And the energy of these flares is extreme. The total power in this superflare star is more than 100,000 times the energy budget of any other known superflare star. That's a big jump. These superflares are undoubtedly caused by magnetic reconnection, the same basic mechanism as we see on solar flares and flare stars, but the humongously larger scale presents a very difficult challenge for astrophysics theory. How can you get such huge magnetic fields and have them annihilate once a day? Some of the implications of these superflares are that, well, superflares would kill all life on surrounding exoplanets. Okay, so let's give the longer version of it. Well, Nova Ophiuchi was discovered in 1998 by an amateur astronomer. Soon thereafter, Dr. Pegnoda was suspicious that this might actually be a recurrent nova. And so she went back and checked all of the world's supply of old astronomical photos. And she found on a plate taken at Harvard, or now stored at Harvard, from the year 1900, she found a prior eruption. So this star had a nova eruption in the year 1900 and 1998. Hence, it becomes a recurrent nova. It's the 10th known recurrent nova. And recurrent novae are the rarest form of variable stars that we know of. To give a little bit of background for this system, we have, well, like all novae and recurrent novae, it consists of two stars in orbit around each other. One of the stars is relatively normal, and but it's in a close orbit around a white dwarf. Now, it's in such a close orbit that matter falls off of the normal star onto the white dwarf, and it's mediated through this large flat circular accretion disk. Now, the companion star is actually rather similar to our own sun, but it is spun up because of the orbit. It's spun up to a 1 1/4 day rotation period. And because of that, the companion star must have very high magnetic fields, high activity, and large and plentiful sunspots with them. Well, the superflares were discovered with the Kepler data, the Kepler spacecraft. And in the upper left is a light curve showing brightness as a function of time. And you can see that the first week or so, there wasn't much in the way of activity. And then you started getting superflares. These are short-term brightenings, well isolated in time, that just keep trucking along. These superflares have a typical duration of about 1 hour, typically like that. They vary up and down in brightness. The brightest of them all happens to be this one right here. And we can go calculating what the energy of them is. And the energy is 2 times 10 to the 39 ergs, fine. It might be more convenient to use another alternative unit of energy here. And an appropriate one would be what I would call a Carrington. Now, this is, so 1 Carrington would be the energy that would correspond to the notorious Carrington event of 1859, the all-time high, most energetic solar flare ever seen. And so the energy in this highest flare is 20 mega Carringtons. That's 20 million, the energy of 20 million Carrington events. That's a lot. Let me give you a little bit of background for superflare stars. Well, superflares are very high energetic flares, presumably with the same mechanism as solar flares and flare stars. But superflares are distinguished because they have much higher energy than one would ever possibly expect from a normal star. And so the lower limit I would place on what a superflare is it has to have more than like 100 Carringtons. Okay, now these superflares were discovered and named back in 1989 by myself. And the realization was that these superflares are have no regular explanation. They're past all experience, and they're seen on all types of normal stars. Everywhere in the HR diagram, superflares have been found. Now, these superflares are undoubtedly caused by magnetic reconnection. Again, it's the same mechanism as for solar flares and for flare stars. And in the case of V24870, I have an illustration off on the right showing what we think is going on here. Well, here you have the same base picture of the system, the normal star, the accretion disk, and the white dwarf. Now, because the companion star is so fast rotating, there are many magnetic field lines depicted in green. Now, these field lines are going to get tied to the gas, and some of the gas is going to be spilling over onto the accretion disk, which is going to go carrying the footprint of these magnetic field lines with it. And once they start getting in here, get tied to the gas and the accretion disk is going to rotate them around and around, and they're going to get twisted and folded and amplified and stretched. And so there are going to be points in here where the magnetic field lines are going to go reconnecting. They're going to change their connectivity. And when they do that, they go to a lower energy configuration, and the reconnected field lines release huge amounts of energy. All the energy is in the magnetic field, and this energy will come out as optical light. Well, it also comes out as X-ray to radio light. We've seen those. But generally, we're looking in the optical, and so we're only seeing the optical portion of the superflare. The consequences of superflares are, well, for life on exoplanets around a superflare star, the consequences of superflares are horrific. There are multiple ways at which superflares have of being able to destroy all life and technology within any planet in one of these in a superflare star system. One of the most general ways is that a superflare radiation is going to go stripping off all of the atmosphere from all the planets. And not only will it strip off all the atmosphere, but then any surface water or any water is going to go away, go into the atmosphere, and then get stripped off also. So superflares are going to get rid of all of the liquid and the gas components around these stars, which means that you can't develop life there, or if there had been life there, it would rapidly go away. So the consequences of superflares are horrific for life on exoplanets. Now, V24870 is by far the most extreme superflare star that we know. In terms of the time interval, well, superflares happen roughly once a day, and this is over 10 times more frequent than any other known superflare star. In terms of energy per flare, 20 megacarringtons is hard to beat. Well, it turns out there are some superflare stars known, very rare, they don't happen frequently, that have up to about 1 megacarrington. So V24870 has more than 10 times as much energy per flare as any other known superflare star. Now, you can also ask the question of the flare, the total power going to flares, or the energy per year. That is how much energy you generate in a year. And for V24870, that's 1 gigacarrington. What a unit. 1 gigacarrington, 1 billion carringtons every year being pumped out by this star. And the reason it's, and this is much greater than any other superflare star, because in V24870, the maximum brightness, maximum energy superflares are happening very frequently, whereas in other stars, the peak energy superflares happen very rarely. So what you have is the power coming out of V24870 is greater than by over a factor of 100,000 times the yearly energy budget of any other known superflare star. So V24870 superflares are startling. Nothing like this has ever been seen or imagined before. V24870 superflares are by far the most powerful known. They're over 100,000 times more powerful than any other known superflare star. V24870 superflares are, Well, now a very hard challenge for theorists. You have to go making magnetic fields of 10 to the 7 Gauss over large volumes. And then you have to go reconnecting them to get rid of that magnetic field energy to create this superflare. And you got to do this once a day. This is a hard problem. And V24870 superflares are bad for life on exoplanets.
All right, so it looks like it's time for the Q&A. We can start with a question for Andrew. This comes from Bill Waller of the Galactic Inquirer. What made you choose the M67 cluster? It happens to have the same age and metallicity as the sun.
Yes, it does. So that makes it very popular for studies like this going back decades. So the reason we chose M67 it was because it was also happened to be in the field of view of Kepler, more specifically in the K2 campaign. So when Liner et al. 2019 first discovered the blue lurkers, they did so based on their rotation periods, which were measured based on the light curves obtained from Kepler K2. So there are also a few other open clusters observed in K2, most notably M35, which is 150 mega years old, very young, and also NGC 6819 and 6791. So there are future targets for searches for more blue lurkers.
Okay, great. I'll go ahead and follow up with another question for you, Andrew. This one's from Camilla Carlisle of Sky and Telescope. Apologies if I missed it, but why are these stars called blue lurkers?
Yes, so the name blue lurkers was coined to connect them in spirit to the classical blue stragglers. It's a bit of a misnomer because blue lurkers aren't blue, or at least no bluer and no hotter than a typical main sequence star. So you can really only pick them out based on their rotation periods.
Okay, well, I'll go ahead with another question for you because it leads very well off from that one. So this one is from Rick Feinberg of the AAS. What is the connection between blue lurkers appearing young and them being low luminosity analogs of blue stragglers? Are lurkers and stragglers related in an evolutionary sense, or are they two distinct classes of objects that just have some similar properties?
That's a very good question. So, yes, so as of right now, we believe that blue lurkers and blue stragglers form through similar pathways. So in that sense, they share a similar history. Now, whether or not a blue lurker will become a blue straggler, that's hard to say. So in the instance of WOX 3001, which is already very close to the main sequence turnoff, if as the cluster ages for another gigayear or so, it might appear as a classical blue straggler. But in the case of WOX 14020, it's more difficult to say.
All right, thank you. Our next question is for Samuel Swihart. It comes from Camille Carlisle of Sky and Telescope. Are you able to estimate how long ago the star became a white dwarf?
Yeah, so first, the simple answer to that question is technically it's not a bona fide white dwarf yet. And that's kind of the idea of this system is that it's a precursor to a white dwarf. So in about 2 billion years, it will look identical to most of the white dwarfs. But right now, its radius is about 5 times larger. This could be related to the question about when did mass transfer end, and that's a little more complicated. We could think that probably ended within the last billion years or so. But the short answer to the question is it's not a white dwarf yet. It's kind of a puffy white dwarf. Imagine a white dwarf that still has a very bloated outer envelope.
All right. Thank you. Our next question is for Brad. It comes from Rick Feinberg of the AAS. Are all superflare stars in binaries, but only some of them, like V24870 in systems with white dwarfs? Could the presence of the white dwarf, as opposed to a normal star companion, be the reason for the extreme nature of the system's superflares?
The extreme superflares really have to be related to the mass transfer and the recurrent nova nature, because you have a very sharp dichotomy here. You have previously all known superflare stars are on what you could call normal stars. And here you have all of a sudden something that's 10,000, 100,000 times bigger appearing in the only superflare star that has these accretion disks. So there's got to be a connection. So somehow or another, the extreme superflares have to be associated with this, with the accretion disk. A plausible scenario, but not forced at this point, is that you have the magnetic fields from the necessarily high magnetic fields around the sunspot, star spots in the companion star. Some of them gets, the magnetic field lines get anchored to the gas, which then spills over onto the accretion disk. So that would then provide a seed field, and that's a very natural way at which you can go getting magnetic lines connecting star spots on the companion star down to the accretion disk. Once you have that, then the thing, then the accretion disk is rotating around once a day, and it's just going to go twisting and amplifying and making that magnetic field strength much larger. The presence of the white dwarf. Well, white dwarfs are very well known to have often very high magnetic fields. And in this particular case, we have reasonable reason to know that the white dwarf actually does have a fairly high magnetic field strength. But it is unclear how the magnetic fields from the white dwarf are going to get out and become part of this magnetic reconnection. It could well be, but is not necessary. Basically, the configuration of the magnetic field lines is not known. We have plausible ideas, but it's not known in this case of what's going on.
Okay, thank you. We have another question for you, Brad, from Ethan Siegel of Starts With a Bang. V24870 is a supremely active recurrent nova with, I believe, an 18-year recurrence period. When you're talking about this as a superflare star, what do we think is going on, not only with one star, but with the entire likely complex stellar system that's causing these rapid, frequent super Carrington events? Can we model this and reproduce what we see?
Well, I'm not sure what you mean reproduce what we see. One quick answer is that the best analogy or the best analog computer for the system would be the sister recurrent nova U Scorpii, which nominally has the same orbital period, the same masses, the same everythings. But U Scorpii certainly does not have superflares on it. So at some level, there has to be something different going on between V24870 and, well, basically every other known cataclysmic variable or nova or recurrent nova. There's something else going on in this system, and we can't really say what it is. There's an analogous problem for standard superflare stars, which is that, well, for example, looking at sun-like stars, something like TESS has shown that something like 1.6% of stars that are close solar analogs, 1.6% of them have superflares. But now that means that 98.4% of the stars, like our own sun, don't have superflares. And you look at these stars which have superflares, and you look at our own sun and other stars like it, and we don't have a ready difference between the two. So there's some other property going on in there that we have not yet worked out that is making for some stars having superflares and others not. And V24870 has the similar sort of problem between something rare is going on in V24870 that is not going on in all of the other nova, recurrent nova, and cataclysmic variables.
I just want to follow up on that, Brad. So are you saying that there's a dichotomy between the stars that have superflares and the stars that don't? Or could the sun, for instance, become a star that has superflares in the future?
The question of whether there's a sharp dichotomy is one that we don't have an answer to right now. A variety of models for superflares would have there being a sharp dichotomy. For example, our sun does not have a close-in hot Jupiter, hence it cannot have superflares. Well, okay. So you're kind of skirting the question that might be in the back of many people's minds about our own sun and superflares. Shame on you. And the best answer there is that, well, no, we have no theoretical reason why our sun should be part of the 1.6% of stars which have superflares, whereas the 98.4% don't have superflares. Fine. We actually do have reason, however, to know that our sun, observational reasons to know that our sun has not had superflares. Probably the best way of looking at this is to look at the tree ring record, which goes back now 11,000 years. And you can look at radionuclides in each little tree ring section. And if a superflare happens, you should see the effects of that in the tree rings. And so you can identify large effects. And what you find is that the superflare, or the largest amplitude flare in our own sun over the last 11,000 years is only a little bit more energetic than the big Carrington event. And so, 11,000 years, we never really got much above the Carrington event. That shows you, because all of these things are very much on an e⁻² power law. And so if you don't have, if you only have a Carrington event once every couple centuries, to get a 10 Carrington event, it's going to be a long time, and to get a 100 Carrington event to get up to superflares is a very long time. So the answer is, we actually know that our sun does not have superflares at anything much larger than the Carrington event. And you got to be careful here about these superflares. Many groups and, let's say, popularizers are pointing out this possibility that our sun might have superflares. Well, the best evidence is ain't no way, no how, but it's an exciting possibility. And I think we should minimize this possibility because it's overlooking a real known and horrific effect of the Carrington events themselves. We know our sun has Carrington events. They happen once every century or two or three. And if one happens now, upcoming, it's not looking good for modern civilization and technology. And there are things we can do about it. You have to harden power grids. You have to harden satellites. And that's where the real problem comes. And so we should not let superflares on our own, the possibility, the very far unlikely possibility of superflares on our own sun, we shouldn't let that take away from the horrible, real, upcoming inevitability of an ordinary Carrington event on our sun.
Oh, thank you for simultaneously making me feel better and then much worse. Sam, I had a question for you. So you mentioned that you got the radius of the star and you didn't go into detail there, but I'm curious how that works.
So that's actually pretty simple. We know how bright the star is. That's the easy part. You just measure it with a telescope. How bright is it? So from the Gaia satellite, which measures the precise positions of all the stars in the sky, we know its distance very well. So if we know its brightness, how bright it appears to us, and we know how far away it is, we now know what its luminosity is, how intrinsically luminous it is. And I showed you in one of the slides that we have an estimate for its temperature. So if we have an estimate for its intrinsic luminosity and then an estimate for its intrinsic temperature, there's a very simple relation that relates to the radius of the star. So there's really just three things. We have its apparent brightness, its distance, and its temperature. And if we have those three things, we have its radius. And in this situation, the radius of the companion is about 25% that of the sun. And that's how we know that this is a proto-white dwarf, because a typical white dwarf will only have a radius that's about 5% the radius of the sun.
Got it, thanks. And just out of curiosity, do you have plans to, I realize this is maybe a little coincidental, but do you have plans to try to hunt for more sources like this? Is it possible that any of the other unidentified Fermi sources, for instance, could be similar things.
Definitely. We're doing that right now. And actually, as part of NUAR's Gemini telescope, we have an active program ongoing that's doing similar spectroscopic observations, following up these unidentified Fermi sources to try to find just these kinds of things, these millisecond pulsar binaries in these interesting parts of their evolution.
Awesome, thanks.
All right, well, I have a question for Brad. When you're talking about these extremely strong superflare events, you did mention a few times the dangers in terms of habitability. When the events are this powerful, is that something that could be a concern for like nearby stars potentially hosting planets, or is it no? Okay.
No. 1 over r squared is a very powerful thing when you're dealing with interstellar distances. So the superflares will sterilize outer and inner planets, but they won't sterilize the next star system over.
Okay, thank you. Well, that's all the questions that have been entered in the Q&A box. Is there anything else?
I don't see any on YouTube, so I think we're good to wrap things up.
Great. All right, I just wanted to thank all of the speakers for their very interesting science talks, and thank you to the audience for your great questions for the speakers. Thank you to the PIOs who helped with the press releases and the briefing prep. Thank you to USRA for sponsoring this press conference. Our next press conference will be at 2:15 Mountain Time or 4:15 Eastern, called Mapping Local Structure and More Evolving Stars. So we hope to see you all there.